In this video, we are going to find the inverse Z transform using the power series expansion method. The example that we need to solve is as shown. Let me just choose the color. So, the example is given as find the inverse Z transform of the signal x of Z, which is Z square into 1 minus 1 by 2 Z raised to minus 1 into 1 plus Z raised to minus 1 into 1 minus Z raised to minus 1. So now what we can do is we can just retain Z square as it is, and then we are going to have 1 minus 1 by 2 Z raised to minus 1 as it is. You can see here that this is of the form a plus b into a minus b. So the answer is a square minus b square. So it is going to be 1 minus z to the power minus 2. If I try to open the bracket, this is going to be z square minus 1 by 2 z, and the second bracket is intact, 1 minus z to the power minus 2. So once again, if I remove the brackets, the first time getting multiplied gets me z square, and minus half z into plus 1 is going to be minus 1 by 2 z. Z square into minus z square is going to be minus 1, and then minus of minus is going to be plus. Half z into z to the power minus 2 gets me half z to the power minus 1. So this is the equation we are getting now. So you can see here that the power of z is 2, here it is 1, 0, minus 1, so on. So we know the standard equation of z transform, which is given by summation n is equal to minus infinity to plus infinity x of n times z to the power minus n. So just by merely comparing with this equation, we can write the value of x of n as shown here. So x of n is equal to, now if you look at the power of z, it is 2. So the value of n must be minus 2. It is minus 2 because when you put n is equal to minus 2, minus of minus 2 gets me 2. So that is how I have z is to 2. So its coefficient is 1. So I'm going to write it as x of n is equal to 1 when n is equal to minus 2. Coming to this particular term, the power is 1 here, hence the value of n must be minus 1. So its coefficient is minus half. So I'm going to write it as minus half when the value of n is equal to minus 1. If you look at this term, the coefficient of z is 0. So power of z is 0 rather. The coefficient is minus 1. So we will write it as minus 1 when the value of n is equal to 0. If you look at this term, the power of z is minus 1. So this corresponds to the value of n equal to 1, and its coefficient is plus half. So this is equal to 1 by 2. For all other values, the answer is 0. So I would write it as 0 otherwise. So this is the required answer. Alternatively, you can also indicate this answer as x of n is equal to delta of n plus 2. Why delta of n plus 2? Because I know that delta of n plus 2 exists only at n plus 2 equal to 0 or n equal to minus 2. So at n equal to minus 2, the coefficient is 1. That's what I'm trying to write here. Then what about this? Now this is a signal corresponding to delta of n plus 1. So delta of n plus 1 exists only at n equal to minus 1. So its coefficient is minus half. So I'm going to write it as minus half times delta of n plus 1. Next, at n equal to 0, the coefficient is minus 1. So I can just write as minus delta of n. At n equal to 1, the coefficient is half. So I can write it as plus half delta of n minus 1. So this is the required time domain signal corresponding to the given x of z. Please note here that there is no ROC given here. It is not necessary because this signal has the negative side as well as the positive side. So using this power series expansion method, you'll be able to find the required discrete time signal as x of n as shown here. Thank you.